So in the last video, we talked about the different forms of quadratic functions and what information you can get from each different form. And in this lesson, we're just going to really quickly look at an example for each of those. So this is from page 179, and I'm going to just do numbers 1, 2, and 3 because it gives me standard form, factored form, and vertex form. So what I'm going to do is use those notes that we took when we're looking at each of these problems. So I think that everybody should always use a separate sheet of paper because then you have more space. But for the sake of this video, I am going to write directly on the workbook so that we can see everything that I'm looking at one time. So number 1 is f of x equals x squared minus 6x plus 8. So I know by looking at this that it is in standard form because it is in the form f of x equals a x squared plus bx plus c. So I'm just going to write down the function in question directly beneath my standard form. I am first asked to identify the y-intercept. I know the y-intercept is just 0, whatever my constant is. In this case, my constant is 8. So we know our y-intercept is 0. I'm going to write it on this side. 8. Now it's asking me to identify the vertex. Remember, our vertex has a specific formula, which is for the x value, x equals negative b over 2a. So what I'm going to do is plug into that equation, negative b, my b value. And this is what I like to do in order to make sure my signs remain consistent. So I have negative, whatever b is negative 6 in this case. And then a is just 1. So my x value of my vertex ends up being negative times negative, so a positive 6 over 2, which gives me 3. 3 is just the x value of my vertex. I need to go back into my original equation, so back to x squared minus 6x plus 8, and plug in 3 for x. So I'm doing my parenthesis method to make sure that I don't mess anything up. And I put in 3 for each of my x values. 3 squared is 9. Minus 6 times 3 is minus 18 plus 8. Then I just need to simplify. 9 minus 18 is negative 9 plus 8 gives me negative 1. So if that's the y value of my vertex, now I have my vertex because I have my x value and I have my y value. So it's 3, negative 1. And I know that this is a minimum because my a is positive. It's a positive 1. So I know my graph is going to open up, which means that I have a minimum value for my vertex. Oh, I just answered letter C. So identify whether the function has a maximum or a minimum, and has a minimum. So that's how we can use our information from standard form. Next, we're going to do number 2. Number 2 is f of x equals negative 0.5, in parentheses x plus 2, and another set of parentheses x minus 4. So we are going to examine that portion, which is factored form. So we have our two sets of parentheses, which means I have it in factored form. So if I am identifying the x-intercepts first, remember all we have to look at, since they factored it for us, is each set of parentheses. So I've got x plus 2 equals 0, and I've got x minus 4 equals 0. I just have to subtract 2 from both sides, and I get x equals negative 2. Here I add 4 to both sides, and I get x equals 4. So I pretty easily found my x-intercepts. For both of those x-intercepts, we know that their y value is 0. So I'm going to write this as negative 2, 0, and 4, 0. That's for our x-intercepts. My y-intercept is a little trickier to find because I'm actually going to have to rearrange this format to be in standard form to find my y-intercept. So I can do that, or I can just substitute in 0 for x and simplify. So that's actually what I'm going to do. So I know that my x-intercept has a y value of 0. So if I have my factored form, I know I'm just finding f of 0, which means I've got negative 0.5, 0 plus 2, and then 0 minus 4. I'm going to do what's in parentheses first. So I end up with 2 and negative 4. I'm going to do 2 times negative 4 and get negative 8. And then negative 0.5 times negative 8 actually gives me positive 4. So my y-intercept is going to be 0, 4. So right here, this time, I'm going to write 0, 4. My axis of symmetry, I just need to think about what my notes say. My notes tell me that p plus q over 2 gives me my axis of symmetry. So I am going to do this in a different color so we can kind of tell things apart. And I know x plus p, x equals p plus q over 2. So that means, so p is going to be negative 2 because it's really just our two zeros. So I've got negative 2 plus 4 over 2, which gives me 2 over 2, which gives me 1. So my axis of symmetry is at x equals 1. And then my vertex, we are just going to plug into our function just like we did with the 0. We're going to plug it in as 1 and solve for f of 1. So we're going to do f of 1 equals negative 0.5, 1 plus 2, 1 minus 4. F of 1 equals negative 0.5, 1 plus 2 is 3, 1 minus 4 is negative 3. We're going to get f of 1 equals negative 0.5 times negative 9. And I know that a negative times a negative is going to give me a positive. And that positive number is going to just be half of 9, which is 4.5. So a little bit more steps here, but we've got 4.5. So I know that my vertex is 1, 4.5. Now we're going to look at vertex form a little bit more in depth than the other two examples just because we've worked with those before. So vertex form is in the format f of x equals a, x minus h, in parentheses squared plus k. So I know, given this information, what my vertex is and my axis of symmetry, but I want to be able to look at this in a little bit more useful form. So what I'm going to also do with this example problem is I'm going to rearrange this equation into standard form so that we can look at it just like standard form. So we already know how to do that with factor form, which is why we're focusing in on using it with standard form. So the example I'm going to do for this one is from page 179, and it's number 3. So what this problem looks like is it says f of x equals negative 16 x minus 1 squared plus 10. So just looking at this, I have all the information I need that it can provide just by looking at it in this format. So I know that minus h, it's a subtraction sign, and then whatever this value is my h, which is my axis of symmetry, and it's my x value of my vertex. And then it's also the x value of my vertex. And then my my y value of my vertex is just whatever that constant is we're adding at the end. So my vertex is just 1, and then whatever number I'm adding to the end, 10. So that's actually really easy if we're given it in vertex form. And looking at this, I know that it has a maximum because A in this example is negative. And remember that a negative A value means that my graph opens down, which means that I have a maximum. So that is actually all of the questions that it asks us on page 179. But I also want to show you how you would just rearrange this equation to be in standard form. So f of x equals negative 16. What I'm going to do with this parentheses is instead of having an exponent of 2, I'm going to just write it out in expanded form. So I know that squared means that whatever is inside of parentheses is being multiplied by whatever's inside the parentheses. So I know I'm just multiplying x minus 1 by itself. So then I don't have to deal with this exponent. So now it just kind of looks like standard form. We just have something we need to add at the very end. So we're going to, it looks like factored form. We're going to multiply my first term by the first term here. So I'm going to get, I'm going to make that a parenthesis. X times x is x squared. X times negative 1 is negative x. Negative 1 times x is also negative x. Negative 1 times negative 1 is just positive 1. Don't forget about your plus 10, but I still can't look at that because I still have parentheses. I'm going to combine my like terms. And now I'm going to distribute my negative 16 to each term in the parentheses. So I'm going to get negative 16 x squared plus 32 x minus 16 plus 10. And now I care about the 10. So now I'm going to, I'm going to move this up. Just combine these two like terms. So negative 16 x squared plus 32x, and then negative 16 plus 10 is just negative 6. So now I have that vertex form of my function in standard form. So that just makes this a little bit more useful than just identifying the axis of symmetry in the vertex and whether it opens up and down. It gives me just a little bit more to work with, but this is really easy information to pull out right away.